My name's Jim Thomas, and I'm a professor of bioinorganic chemistry. I'm kind of in the interface between coordination chemistry and biology. We're interested a little bit in self-assembly. We're particularly interested in compounds which are photoexcited. And the aim of the work is usually to make sensors or probes for anion, bioanions, biomolecules, things like this. So that kind of leads to things like cell probes or even therapeutics, or to be more trendy, an area called theranostics, which is, diagnostics and therapy all rolled into one. My philosophy is I don't like making things just for making things, so I do like to make things for some reason. So I'd like to think that in long term we could, contribute to producing something that makes a difference for instance, in treating cancers or something like this. I mean, we have got some compounds which, if you asked me 20 years ago, I wouldn't believe this, but we've got some compounds now which are beginning to get to the point where they're going to be tested with animal models and things like this. So, so they are actually genuinely therapeutic leads. There's kind of two ends to it, really. We've got one set of systems which are based on self-assembling quite big structures, architectures, which can be used to bind to DNA or other bioanions in unusual ways. So like, for instance, we've got one system that self-assembles and it kind of binds to DNA in a way that only one other thing binds to DNA that way, and that's a transcription factor which is involved in reading DNA when it's converted into RNA. So that's quite interesting. And then on the other side of things, we're making very simple substrates that bind to those kind of DNA structures that duplex DNA very simply through stacking between the bases and things like this. And some of those are just for visualizing DNA within cells and things like that. And some of them have been designed so that they're either intrinsically cytotoxic, so that they're not only can you see them, but they damage DNA in a way that produces a therapeutic effect. It's rewarding, it's creative. I hope you're doing something, well, hopefully you've signed up for a project that you find interesting. So, you're basically doing something that you like, but 9 to 5, you get paid for it. It engages you mentally, and it's very different from being an undergraduate, because as an undergraduate, obviously you need to learn the basics of chemistry to be able to move forward, to be actually do research. But research is a very different process to just learning about science. It's the difference. You actually become actively doing science, and so that's a much more, in my opinion anyway, it's a much more engaging process than sitting down and learning a lot. But like if you want to read a book, you have to learn the alphabet. So there's always tough stuff to do before you can do the really interesting thing. If you want a job in most of the chemical and pharmaceutical industries, it makes a big difference if you've got a PhD. One thing is that quite often people don't realise that how international research science is, and how all the people in this department have an international reputation. If you were to go to Germany and mention some names, of people working in Sheffield, people would know them. And the other side of that coin is that if you are working in research, it is in an international community, so you do get to travel a lot, and you will have people from all around the world working in labs, and you may find yourself somewhere else in the world working with lots of different people. So a PhD can be a passport to international travel as well.